Hi, my name is Yannis and I am a software architect working for Atos in Athens, Greece. Today, we're going to talk about software quality. Here is a screenshot from the software application that I work on. It is called Common Management Platform. It is a web application based on Java Stack and it's been around for more than 10 years. It is a web application that enables our customers to automate common administrative tasks, allowing them to spend less time in provisioning and configuring our products. All the examples, all the figures, all the data that we are about to see are actual ones and they come from this software application. How do we know when a software application has quality issues? Well, this is usually obvious because everyone keeps complaining. Customers complain about the bugs that they keep finding. The development team also complains that the bugs are too hard to fix. And it takes them too much time to implement new features and extend existing functionality. Although it's obvious when we have quality issues, it's less obvious what we need to do in order to fix them. I've heard someone saying that we need a superhero developer to do wonders in order to fix our defective application. That's what we need to do. Is it? Of course not. As we are about to see, there are 5 simple, practical steps that you can follow in order to improve the quality of your software application. Even if you are a junior developer that just started your career, you can do this. Let's see. How do we measure the quality of a software application? We do this by counting the number of customer tickets for every month. As you can see from this graph, we have 2 lines, the blue line and the red line. The blue line depicts the total number of customer tickets that were opened for our application. But not all of them are actual bugs. Some of them are due to a misconfiguration of our application or due to a misunderstanding of how our application really works. It's the red line that shows us the actual number of bugs that we had to fix, the ones that we had to provide the solution to the customer. And there are also those black lines that show us the trend. In our case, the number of customer tickets has a falling trend. They're continuously falling. So it seems that we continuously improve the quality of our product. If this number increased, then we would know that we have issues with the quality of our software application. Still, this is a way of measuring quality after the application is deployed, after the application is shipped to our customers. What can we do proactively to measure the quality before our product gets delivered to our customers? That's why we have an extensive suite of automated end-to-end tests based on Selenium. We have been constantly trying to increase the code coverage, for example, increasing it from 67% to 72%. These tests, these automated tests, act as a safety net. So when we make changes to our code, we know that these tests will identify potential problems. It will identify broken functionality and help us fix these issues before our product gets delivered to the customer. But although we are striving to increase our code coverage and write more and more tests, we've noticed that the more tests we have, the more time it takes for us to run them, the more time it takes for us to evaluate the results, and the more time it takes us to maintain any tests that may break. So we're looking for a balance between the code coverage and the effort that we have to spend in order to run, evaluate, and maintain these test suites. Stay with me and we will shortly see what we did in order to find this balance. What else can we do in order to further improve the quality of our software application? We've been using a static source code analysis tool called SonarCube. It looks for bad coding practices in our code, and when it finds them, it classifies them into different categories such as bugs, vulnerabilities, and code smells. It also estimates the number of days that we will need as software developers in order to fix all these issues, in order to pay off this technical debt. As you can see, we spent a lot of effort in order to decrease our technical debt from 1,359 days to 392 days. That's a lot of effort. Was it worth it? Should you also do the same thing for your application? Well, my experience tells me that you shouldn't do it. Although I personally enjoyed fixing all these issues, although I enjoyed cleaning our code and rewriting some parts to make it more readable, I've changed the behavior of our application and broke its functionality, not once, not twice, but quite a few times. So, why did we do this? We wanted to improve the quality, not to introduce new defects. So something did not go well there. Why did this happen? Because old code is reliable code, and you should never ever touch old code. Chances are that you will introduce defects into your code. That's what happened to us. Even though the code may not be as clean, maybe it's not good looking code, but the code works. Why is it old code in the first place? Because it works. Nobody had to change it. It has been running in production for many years and our customers did not complain. They didn't find any issues with this code. Because it works. So remember, next time you see some old code, you must resist the temptation of trying to clean it and rewrite it if you don't really have to do this. According to the cited research, if we have two modules, A and B, and module A is 1 year older than module B, then it will have 33% less chances of being defective. So remember, old code is reliable code. If you don't have a true need to change it, don't do it. And as the saying goes, if it ain't broke, don't fix it. Let's forget about old code. Whatever happened in the past stays in the past. Let's draw a red line with the past and do our best from now on as software developers to write code of the highest quality. How can we do this? We are using a tool, a plugin that is installed in our IDE that checks our code as we are typing. This tool is called SonarLint. It supports all the popular IDEs such as Eclipse, IntelliJ and Visual Studio Code. It is free and it supports several languages such as Java, JavaScript. So you can also install it. It doesn't take more than 5 minutes for you to do it, and it will be helping you every single day that you write code. Personally, I have been using it for the past year and it has helped me a lot. Every day I learned about bad practices as I typed code. Bad practices that I wasn't aware of, so it helped me become better. That's why I highly recommend that you also install it in your IDE, because it will help you become better developers and write better code. As you can see, when it finds a mistake in your code, it tells you what the mistake is and how you should fix it. It tells you what is the recommended practice. We also wanted to have a central way of checking that our development team does not introduce any technical debt. So each developer can have this plugin installed in their IDE, but we also needed some better way of enforcing a policy that would not allow us to introduce new technical debt. And we did this with SonarCube and quality gates. So whenever a developer pushes new code, our continuous integration, that is Jenkins, will compile our code, and next it will trigger the static code analysis with SonarCube. If SonarCube identifies that we've introduced one or more mistakes in our new code, it will not let us proceed merging this code into our main line. And we achieved this via this feature called quality gates, where we configured them so that we are not allowed to introduce any new bugs, new vulnerabilities, any major or minor issues. You can do this as well if you already have SonarCube. It's straightforward. And it will help you, it will prevent you from not introducing new technical debt into your software application. It's quiz time. How do we spend most of our times as developers? What do we do the most for each day? Do we spend most of our day reading existing code? That's the first option, A. Do we spend most of our time writing new code? That's B. Do we spend most of our day waiting for a full build to complete? That's C. Or do we spend most of our day in other activities, such as meetings or drinking coffee? Please share your answers in the comments. I would love to see them. Our experience tells us that we spend most of our time as developers reading existing code and trying to understand how it works. What is the business logic? Why was it implemented this way? That's where we spend most of our time. So let's think for a moment. Are there some parts of our code that we read most often compared to others? Are there some classes that you have to open every single day and look at them and try to understand again and again what they do? If you are a senior developer in a product, then you surely know which classes you have to open every single day. But even if you are a junior developer that just joined a new team, there is an easy way to find out which parts of your source code are read the most often. Which parts of your source code are absorbing most of your energy, most of your development effort. And you can do this, you can find out which files are the most frequently read files by using the information that is available in your source control system, in your version control system. That is Git. Why do we read a part of our code? We need to understand it so that we can modify it in order to fix a bug or to implement a new feature. So eventually we read a part of our code to be able to make changes to it, to commit a new change to our version control system. So if we measure the number of commits for each file in our repository, then we can implicitly tell which files absorb most of our energy as software developers. This is an actual list of the files in our repository, showing the files with the highest number of commits. As you can see, this is a very simple command in Git that you can also copy-paste and execute for your own application and find out the files with the highest number of commits. Clearly, the first two files are properties files. We use them in order to localize our application in German and English. We shouldn't really care about these files for the moment. We care about the Java files, the Java classes. As we can see, the third one has 227 commits and the fourth one has 205 commits. Practically, this means that every single day, one of our developers needs to open this file, read it, try to understand it, and then change it. So these files act like a bottleneck for our development teams. Imagine two or more developers making changes at the same time. All the merge conflicts, all the time that they need to spend in order to solve these conflicts. We extracted this list of files with a number of commits and imported them into Excel, where we've drawn this graph. What does this graph show us? We have 10,000 files in our repository, 10,000 source files. Most of them are Java files. But only 11 files have more than 100 commits. Only 11 files have more than 100 changes. On the other hand, we have 9,450 files that have less than 10 commits. When a developer joins our team, they see these 10,000 files and they believe that our application is big and complex. But it seems that all the development activities are focused on 11 files, on a limited set of files, and most of the other files are not changed at all. Why does this happen? Is this some weird pattern that only our application has? Well, it's not. This is a pattern that is found in most software applications, both enterprise applications and open source applications. And chances are that the same pattern is found for your application too. So remember, if you need to refactor some files in your application, you don't have to refactor all of the files. You can refactor wisely by aiming only for the frequently changing files, because these are the ones that act as a bottleneck for your development activities. They are the ones absorbing all your efforts. So if you do a well-aimed refactoring, you will spend less time in order to read these files, and you will have to spend less time to extend their functionality. So you will become more productive by doing this smart investment of changing only 11 files, refactoring only 11 files compared to refactoring 10,000 files. There is something more interesting about frequently changing files. According to academic research, frequently changing files are responsible for most of the bugs in our application. That's why we need to focus our quality assurance efforts on these frequently changing files. If we have limited testing resources, we should focus our resources on these frequently changing files. These frequently changing files correspond to some functionality, some features that are also changing. They are also evolving. Whereas files that haven't changed for many years, they correspond to mature functionality, to mature features that haven't changed for a long time. So why should you waste effort testing the same mature features again and again? There is no reason to do that. That's why we must know, we must be aware of which functionality is changing and try to test only this one. Focus our quality assurance efforts on the frequently changing functionality. So the next time that someone comes and asks you, what is the code coverage of your code? You shouldn't care about the code coverage of your total source code. What is important is to have a high code coverage for your new, constantly changing code. You shouldn't care about the code coverage of your mature code. So it's all about asking the right questions and making sure that we have sufficient test coverage for our frequently changing code. It is also important to identify the old parts of our code. As we said, this old code usually maps to mature features, corresponds to mature features. What do we do with old code? How we handle it? In our case, we found out that some components in our code were developed many years ago as some kind of prototype to experiment while implementing a new feature, and they were never run in production. They were somehow dead code. When we found out this dead code, we went ahead and deleted it. And this is what I recommend to you. If you find out that you have dead code in your application, don't hesitate. Go ahead and delete it. And remember, deleted code is the best code. But if it's not dead code, it's just mature code, then it's nice to talk to your product manager, initiate a conversation based on real, actual data, and say, hey, we have these files, these features that haven't changed for the past 10 years. Do our customers still use them? If they don't use them, if the customer's needs have changed and these features are not used anymore, then we should also take a decision to remove this code from our repository. Why should we keep features that are not used anymore? And if we find out that these features are still used by our customers, that's fine, we will keep them. But we should better move them to another repository, to a separate repository, and then use them in our application as external libraries. Like, for example, we treat open source libraries, external jar files. Why would you keep files that haven't changed for the past 5 or 10 years in your repository? If you apply the practices that we just mentioned, you will be able to go faster. You won't spend that much time waiting for your builds to complete. If you're building on your local laptop, for example, as a developer, you will spend less time waiting for the builds to complete. Again, if you're building on your central server, on your CI server, you will wait less for the builds to complete. And you will also gain by faster onboarding of new developers into your team. The smaller your code base is, the more quickly they will become familiar with your code base. They will be able quickly to familiarize and take ownership of the code, to take initiatives to change it and improve it That's why you should really delete old code, delete unused features, and extract mature features into separate repositories and use them as libraries, as third-party libraries. We've talked about frequently changing files, but one other important aspect is their complexity. How do we measure the complexity of a source file? No matter what language you write in, no matter if it's Java or JavaScript or Python, we measure complexity the same way, with the number of lines in each file. So a file that has 10 lines is less complex than a file that has 10,000 lines. Another important metric is the number of tabs or spaces in front of each line. The more tabs we have in front of each line, the more complex our code is. Let's see an example. Have you ever needed to write a nested if in order to solve a customer ticket where your customer had some weird setup that you haven't thought of? This is where we may write a nested if. So if our customer has this exotic setup, then do this and that in order to deal with this scenario. The more nested ifs we have in our code, the more tabs we have in our file, and the more complex our code is. It's more difficult for a developer to read it and understand how the code works. This is the file that we previously talked about, the one with the highest number of commits, 227 commits. The blue line shows the number of lines in this file and how this increased from approximately 100 lines to 6,000 lines, something less than 6,000 lines. The red line shows how the number of tabs increased up to 18,000 tabs. And now let's take a look at our second file, the one with 205 commits. We see that the complexity is much higher, and we also see a steep increase in the complexity. What is that? Let's take a closer look. Back in September 2014, we had to deliver a big, important feature. And there, we increased the complexity from 6,767 lines to 8,396 lines. Likewise, we increased the number of tabs from approximately 22,000 to 29,000. That's a huge increase in the complexity. So if we needed to somehow prioritize our refactoring efforts and couldn't refactor both of these files, then we would certainly go for this file, the one with the 205 commits. This would be our number one priority for refactoring. How can we refactor these frequently changing files? As we said, most of our developers are changing the same files in parallel. This is where our development activity is somehow concentrated. Perhaps I could work on a private branch, make my refactoring there, and in a couple of weeks I can merge the results, I can merge the private branch back to the main branch. But I am afraid that we will have too many merge conflicts, so I will not be able to merge it back. Perhaps we could do something else. I could stop the world and tell everyone in my team to stop working with these files. But is this realistic? Perhaps not. Is there an easy way to refactor one of these complex, frequently changing files? Here is an actual example from our application. This class, named User Management Impl, has accumulated too many responsibilities. Back in university, when we talked about object-oriented programming, we learned that each class must have a single responsibility. But this class has too many responsibilities. For example, it has a group of methods that are related to processing users, adding, editing, deleting, and finding users. There is also another group of methods related to extension ranges, finding, adding, editing, and deleting extension ranges. And last, there is also a group related to finding the assigned phones, fetching a list of assigned phones. Clearly, these methods are not directly related to User Management Impl. When we see a class named this way, we imagine that all of its methods will be related to managing users. So how can we refactor this class? As we mentioned, most of the developers in our development team have to edit this class on a daily basis. So if we attempt to refactor it, we may run into merge conflicts. So here's what we will do. We will create new classes, a new class for each responsibility. In our example, we create user mgmt Java, extension range mgmt Java, and phones mgmt Java. And we copy each group of functions, each group of methods, into the corresponding class so that the new classes have a single responsibility each. We don't delete anything from the main class, the one that is complex and has too many thousand lines. We'll leave it as it is for the moment. We just create new classes and copy all the methods in these new classes. And at the end of the sprint, when most of our developers have merged their changes to the main line, we are ready to complete our refactoring by removing the method bodies from the main problematic class and delegating the method calls to our new classes. So the method signatures will be there and they will be just delegating calls to the new classes. But what do we achieve this way? Why should we spend any time doing this? Because we are actually separating changing code, immature code, from code that doesn't change anymore, from stable code. This is drawn here with the red and blue color. So we try to represent the changing color, the changing code with the red color, whereas the old stable code is with the blue color. So the old stable code is cool, whereas the new changing code is hot due to all the changes that we continuously apply. That's a great tactic to survive in a legacy application. In order to continuously improve the quality of an application, we must separate old code from new code. So this is what we achieved in our case. You can see that the new classes, with each one having a single responsibility, are represented as blue. We expect that they will not be changing in the near future. So we have reduced the surface of the main problematic complex class and have moved a lot of the stable code into new classes. So we're actually dividing our code in our application between old mature code and new changing code. Do you remember Windows Vista? They were released some years ago, back in November 2006. They are one of the biggest software applications until this day. They consist of more than 50 million lines of code, and the development team that worked to implement it consisted of more than 2,000 developers. So Microsoft decided to conduct a research regarding the organizational metrics and how these impact software quality. But let's talk about organizational metrics for a moment. When I first heard this term, I was really confused. What is an organizational metric? First of all, it's the number of engineers that work for a software application. Microsoft assumed that the more people were on the team, the more people touched the code, the lower the quality would be. But why would this happen? It's all about communication. When you have a small team, they can all communicate between them, but as the team size increases and we have more and more people in our team, communication becomes more difficult and we have gaps in our communication. These gaps in our communication translate to gaps in the business logic that we implement. And these gaps in our business logic usually translate to defects in our application. But this again was an assumption. They had no proof until that moment. Another organizational metric is the number of engineers that left the company. When an engineer leaves a company, we lose valuable knowledge, not just about programming, but about the business logic, the domain logic of what the application does. Even if an experienced developer replaces them, they will not be as familiar with the business logic of the application and why it was designed and implemented that way. So they assume that the more engineers we have leaving from a software application, leaving from a team, the more defects we will have in application. Similarly, they talked about the organization intersection factor. So if we have a development team located in America, working on a software application, making changes, when they go to sleep, another team takes over in Europe. They also make changes to the same code. And when they go to sleep, another development team in Asia takes over and again performs changes in the same code base. So they assume that these teams, due to the different time zones in different countries, will not be able to communicate as effectively. And these gaps in communication, again, you guessed right, they create gaps in the business logic and they translate to defects in our application. So what did they do in order to assess if the organizational structure affects quality? They had valuable data about all the customer tickets, all the bugs that were opened to Windows Vista. And on the other hand, they also had valuable data in their source control system about the developers that worked for each component. When they talked about components, they meant executable files, .exe, or dynamic libraries, shared libraries, DLL files. So for each defect that was opened for an executable file, they knew all the developers that performed some commits, that made changes to the code of the corresponding component. And they performed a statistical analysis between the defects for each component and the organizational metrics, the teams, the persons that worked for these components. And you know what they proved? They proved that the organizational structure impacts software quality more than any other factor that we knew. So personally, as a developer, I always cared about writing clean code and about writing code that is not complex, that is easy to understand. I cared about writing unit tests and making sure that I have a sufficient code coverage. Yes, these are still important, but there is something more important than that, and these are the organizational metrics. So you can see that the organizational structure helps us predict the failure proneness of a module, of a software module, with a much higher precision than all the other metrics. The organizational structure has a precision of 86.2%, whereas code coverage and code complexity come next. And you know what? It's usually easier to change the organizational structure than to change the code coverage or the code complexity of an existing legacy application. You can have quicker and more efficient results if you change the structure of your teams working on a software application than trying to write unit tests for a legacy application that doesn't have them. Both are important, but the organizational structure seems to be more important. Microsoft decided to investigate further how these organizational metrics impact software quality, and in Windows 7 they made a distinction between the different types of contributors. So they said, okay, the person who has the most commits, the most contributions to a component, is considered to be the owner of this component, the owner of this executable file, for example. All the developers that have more than 5% of the total commits are considered to be major contributors, and any other developer that has less than 5% of the total commits for this component is considered to be a minor contributor. So what they found out after performing a statistical analysis between the defects that were reported for Windows 7 and the developers who worked for each component, for each module, is that the more minor contributors we have, the more likely it is for our component to have failures, pre-release and post-release failures. On the other hand, if we have an owner with a high level of ownership, then it is less likely to have a defective component. But again, a high level of ownership cannot compensate for the high number of minor contributors in a component. So when we have a lot of minor contributors, then the chances are that we will have more defects in this component. This is an actual chart from one component in our application. As we can see, we had a total of 427 commits for this component, and 87 commits out of them were made from one developer who is the owner of this component, with a total percentage of 20% of ownership for this component. Still, we see that we have 15 minor contributors and only 6 major contributors. So the contribution from software engineers to this component seems to be quite diffused, I would say. But again, these data on their own do not convey a lot of information. So how can we evaluate this data? How can they help us in order to take decisions? Well, here's another component. Let's say component B from our application. Again, this is actual data. We can see that the owner here has an ownership of approximately 29%. We have only 3 minor contributors and 6 major contributors. Again, these data on their own are not really useful. But when we put the data from these two components side by side and compare them, let's have a look. Clearly, component A has more minor contributors, 15 versus 3. Component A and B have the same number of major contributors. And component A has a smaller ownership compared to component B. So if you had these two components in your application, which one would have more defects? Where would you focus your testing efforts? Yeah, you guessed right. The component that has the biggest number of minor contributors will have more defects. And the component that has a bigger ownership will have less defects. So if we had limited resources in order to test our application, then we should certainly spend this effort to test component A, which has more minor contributors and less ownership compared to component B. How can we use this knowledge in order to build better software? First of all, we learned about minor contributors. Minor contributors are software developers who have less than 5% commits in a component. They are not junior developers. They may be experienced developers, but they are not familiar with the business logic of the given component. So we should really pay attention to minor contributors in our software applications. When a minor contributor is about to implement a new feature or fix a bug, we should not wait until the code review. Before taking over a task, a minor contributor should consult with the owner of this component or a major contributor and discuss about how they plan to implement it. So we need to carefully discuss and plan and design before proceeding with the implementation. And when the time comes for the code review, a major contributor, or ideally the owner of this component, should be doing the code review, because we know that minor contributors have a high likelihood of introducing defects into our applications. And when it comes to testing, we should focus our testing efforts on components with low ownership, on components that have a high number of minor contributors. So remember, it's about setting the right priorities. It's not about testing everything. We should be smart and test what is needed the most. The next time that someone comes to you, a customer comes and requests for a new feature to be implemented, but the major contributors or the owner of this component are busy doing something else, what would you do? How would you respond to this customer request? Would you ask from your minor contributors to start implementing this feature right away? Or would you wait until one or more major contributors are available? Would you delay the implementation of the feature or not? If you care about software quality, then you know what you need to do. Here is a simple git command that you can run in order to find out all of your contributors for your component. You can copy-paste this and run it for your repository. As you can see, it displays the number of commits for each developer, and there is also the option of restricting the results after a given date. So if there was a handover and the development team changed, or if the structure of your team changed significantly, maybe you prefer to filter the results after that date in order to find out who your major and who your minor contributors are for a component. So here is what you need to do in order to improve the quality of your software application. First of all, you need to stop creating new quality issues. We've seen how we can do this using tools such as SonarLint and SonarCube, where we set the quality gates. Second, you must be really careful not to touch old code, because old code is reliable code. Third, you must refactor your most complex, frequently changing files, because these are the ones that act as a bottleneck for your software team, for your development team. They are the ones where you spend the most time reading and trying to understand what they do. Fourth, you need to focus your quality assurance efforts on frequently changing files, because these are the ones responsible for all the bugs in your application. And fifth, you need to pay special attention to minor contributors, making sure that you pay attention both to code review and careful collaboration and design before implementing a new feature. What do you do in order to build quality software? Which practices do you apply? Please share your experience, share your practices in the comments, and I will be happy to learn from you and reply to you for any questions or comments you may have. Let's share our knowledge and experience. Thank you.